we are now recording. So this is, I don't know what we'll call this, but this will just be like, I'm just going to do some review and try to figure out exactly the vocab and content and stuff that you've seen up until this point, so that you and I are on the same page vocab-wise and content-wise, and all of that. So I figure out what exactly you've seen and haven't seen and whereabouts to pick up. I think that Ms. Kotson said were doing section 4.3. Is that correct? Was the last thing that you guys had done? Yes? Okay. And so you had done 4.1 through 4.3, I'm guessing then, to this point? And then you did some stuff before that, right? And then you did some like functions review kind of thing before that part? That this was 1 and this was 2, right? Is that ish what you've done so far? Okay. Yeah, that's fine. I'll try to be clear as to where in the book we're coming from. So I'm going to just kind of sketch through starting in chapter 4 with these chapter 4 ideas. So you guys hopefully remember from geometry, you guys did some right triangle trigonometry, right? Where you talked about sine, cosine, and tangent, that if you're in a right triangle, that sine is the opposite over hypotenuse, cosine was the adjacent over hypotenuse, and tangent is opposite over adjacent. And depending on which angle you're talking about, the opposite and adjacent can change, right? If this is angle x and this is angle y up here, sine of angle x is opposite over hypotenuse. Sine of angle y, well, this side is now the opposite, and this side is now the adjacent, right? So we're still opposite over hypotenuse, but notice if they're different sides than they were before. Is everybody okay with that? Kind of remember this from your geometry course. Did we start this trigonometry going back and starting here? Ish? Yes? Okay. So we kind of compacted all that information into the acronym SOHCAHTOA to just kind of, that we use as a mnemonic device on how to remember, like sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, right? The question now becomes, what do we do for angles that are bigger than 90 degrees? Because we can't rely on this right triangle definition if I have an angle that's bigger than 90 degrees, right? So what we do then is rather than defining these angles inside of a right triangle, so we're going to say goodbye to this definition, and we're going to extend our definition to an angle onto the xy axis, where we're going to say that one side of our angle is always going to be on the positive x-axis. We call this the initial side of our angle. And the other side of our angle is going to pivot at the origin and can rotate any number of degrees around the origin. So we'll start at the initial side, but if I say, what if we have an angle of like 110 degrees, Well, we start at the positive x-axis, and then we rotate. So to here is 90 degrees, and then 20 degrees more is going to give us 110 degrees. So now we found a way to kind of define angles that are bigger than 90, and not only bigger than 90, but bigger than 180 degrees, which are impossible to have in a triangle. So like if I have a angle beta, it could be like 210 degrees. So again, we start on the positive x-axis, and we rotate 90, 180, and then 30 more. And then this is like 210 degrees. And even better, we can define angles that are bigger than 360. So like if I take the angle alpha, I can define something that's like 400 degrees. So again, I start on the positive x-axis, and then I rotate 90, 180, 270, 360, and then like 40 more is going to give me my 400 degree angle. So we have angles that are even bigger than 360 we can do. So as big as you want to make them, we just keep spinning around that circle, right? And we can also do negative angles. So I need another spot down here. So gamma maybe is negative 90 degrees. So again, we start on the positive x-axis, but instead of going counterclockwise around my circle, if they're a negative angle, I go clockwise. Like that. So we can hopefully see the advantage of starting to define angles on the xy axis, because it allows us to do angles that are bigger than 90, angles that are bigger than 180, things that are even bigger than 360, and even negative angles now we have a concept for that maybe we didn't have, that certainly was not possible when we were just talking about things inside of a right triangle. Is everybody okay with that terminology? So again, the thing that's changing, we call this the terminal side. I think I forgot to write that down. But that's the end, the other side of our angle is that terminal side. Over here. I guess I should have gone the other way. These are all the terminal sides. The initial side, though, is always on the positive x-axis. So in a trigonometric sense, having this definition, we can we can talk about when are two angles the same, or what does that mean for them to be the same. So when would two angles technically be the same? The answer is going to be when their terminal sides lie in the same position or same place. And we call these kinds of angles coterminal. So example might be 300, let's say 400 degrees and 40 degrees are coterminal. And I'll just demonstrate why that's true. So again, I'll draw my xy axis. And let's draw the 400 degrees first. So here's its initial side. I go 90, 180, 270, 360, and 40 more. So this is my 400 degree angle. And if I want to do the 40 degree angle, We start off on the positive x-axis, and then we go 40 more, and we notice that we're in the exact same position, right? So in a trigonometric sense, we're really kind of talking about the same angle, right? They have different angle measures. We'll call them coterminal, but all the values that we care about, the sine, cosine, tangents, etc., are all going to be the same. Because from our new definition of defining these things on an xy axis, we're really talking about the same picture, right? So is there an easier way to check if something is coterminal? So there's an easier way to check. We can just add or subtract 360 and just keep doing that until the two things are equal. Or if you're working in radians, it would be 2 pi. So for example, maybe we want to check to see if 750 and negative 390 are coterminal. So it doesn't matter which one that I pick. So let's just say we start with negative 390. What I'm going to do is I'm just going to keep adding 360 to it till either I equal 750 or go past 750. If I go past 750, I know that they're not coterminal. If I can make it equal to 750, I know they are. So you may. So I see that by adding 360s, I passed 750 along the way and didn't ever get to 750, so we can conclude that these are not coterminal. Everybody okay with that idea? So whichever way you want to do, you can add to the smaller one or subtract from the bigger one, or do add or subtract to both of them at the same time and try to meet somewhere in the middle. That's all fine, but that's basically all you're doing, is you're just kind of adding and subtracting multiples of 360, or if you're working with radians, 2 pi. And why is that? Because two things are the same if, like, this thing and this thing. Basically all you're doing is eliminating, like, that distance out of there. And how far was that red piece? That's one rotation, or 360 degrees. So that's going to be, if two things are coterminal, you can just spin around a bunch of times, but you end up stopping at the same places. So you're just basically taking rotations out or putting rotations in. Okay, so that's all well and good. What we want to do now is we want to build a way to evaluate sine, cosine, and tangent. For those bigger angles. And we'd prefer to be able to do this exactly. We want to find the exact values. So our tools are going to be the special right triangles. So one of them is the 45-45-90 triangle, whose side lengths are x, x, and the hypotenuse is x square root of 2. And then the other one is the 30-60-90 triangle, whose side lengths are x, x squared root of 3, and 2x. And remember that the way I remember where to put things, well, the hypotenuse is always 2x, but the leg that is adjacent to the 30-degree angle is the one with the square root of 3 in it. And I just remember that they have 3's right there next to each other is usually enough to help me remember where that x square root of 3 goes. It has to go next to the 30-degree angle. That's not the hypotenuse. So, if I have an angle that is a multiple of 30 degrees or 45 degrees, I can use these special right triangles to find the exact values of, sine, cosine, or tangent. So an example, maybe I want to find sine of 120 degrees. Notice that this is a multiple of 30 degrees. So what I do is I'll start by drawing myself a picture of the xy axis. And then I'll draw my 120 degree angle. So the initial side always on the positive x-axis. And then I go 90 and then 30 more. So there's my 120 degree angle. And what I can do from here is I can draw a reference triangle. So when we draw a reference triangle, we're always going to draw from the terminal side down to the x-axis. And since we're drawing it straight down, I know that I'm creating a right triangle. And I know what this angle is going to be, because I know from here to here is 180 degrees. And from here to here is 120 degrees. So what does this spot that we're missing have to be? 60 degrees, right? Because 120 plus 60 gives me 180. Everybody's okay with that idea? And now, since I know that the sum of the angles in a right triangle has to be, or in any triangle has to be 180 degrees, I have 90 for the right angle. I have 60, so this other angle must be 30. And what I have is my 30, 60, 90 triangle. Everybody's okay with that idea? Okay? So, since this is a 30, 60, 90 triangle, I can label it side lengths. So the hypotenuse is, who remembers? Just shout it out. Yeah. And this side that's adjacent to the 30 degrees is x squared root of 3, and this side is x. Everybody's okay with that idea? Okay? Very good. Now, an important observation, though, here is, what quadrant am I in? So over here is Q1. This is Q2. Down here is Q3. Over here is Q4. And I have to remember about whether x's and y's are positive or negative in each of these quadrants. So in quadrant 1, the x-coordinate and y-coordinate are both positive. In quadrant 2, the x's are negative, but the y's are positive. In quadrant 3, the x's are negative and the y's are negative. Quadrant 4, the x's are positive and the y's are negative. So if I look over here in quadrant 2, that's where my angle is. So this piece here is a vertical piece. That corresponds to a y value, so that should be positive x squared root of 3. But this piece here corresponds to an x value, so that should be negative x. So that's an important piece that you have to remember when doing this. So when we draw in our reference triangle, after you've drawn your reference triangle and labeled the side lengths, you have to go back and look at which quadrant that reference triangle is in and decide whether the which of those legs of your triangle need to be positive or negative. So again, the horizontal sides correspond to when the x is positive or negative, and the vertical sides correspond to when the y is positive or negative. Is everybody okay with that so far? Okay. So, notice that, or an important fact that we're going to take advantage of now is that this angle inside the reference triangle is going to give me the same answer as the sine of 120, provided that I've gone and labeled the side lengths with the appropriate signs, S-I-G-N-S, so that I've gone and labeled the positives and negatives. So I can just now evaluate sine inside this little right triangle, and it's going to give me the correct answer for the sine of the 120. So using that reference triangle, I can just do opposite over hypotenuse. And I get square root of 3 over 2. Okay with this idea? Okay, let's do another example, because this is like a super duper important skill. So let's say we want to find cosine of negative 210. So what I want to do is I'll start by drawing my xy axis and drawing in my negative 210 degree angle. So again, we always start on the positive x-axis. And since we're negative, which direction are we going? Clockwise. So we go 90, 180, and then like 30 degrees more. So there's my 210 degree angle. Next thing I do is draw my reference triangle. Which axis do I draw my reference triangle to? Always to the x-axis. So I start at my terminal side and I just draw down. So again, always draw those reference triangles to the x-axis. So the question becomes, to evaluate this, I need to know what this little angle is. So I know from here to here is 180, and then 30 more is going to give me my 210. So that angle must have been 30 degrees, right? That makes this other angle how much? 60 degrees. So what I have is a 30, 60, 90 triangle. The hypotenuse has length 2x. The side adjacent to the 30 has length x square root of 3. And the other side has length x. Everybody's okay so far? What quadrant is the terminal side of my angle in? This is in Q2. So the x's are positive or negative? Negative. And the y's are positive. So the x is positive or negative? The x is up and down, right? The up and down is which way, x or y? Y, so the x should be positive. And the x square root of 3 is negative. Everybody okay with how I've drawn the picture here? So to evaluate cosine of negative 210, I really just need to find cosine of 30 inside my reference triangle. So cosine is opposite over hypotenuse, so it's negative x square root of 3 over 2x, or just negative square root of 3 over 2. How are we feeling about this? Do we need to do some more? Relatively okay? Okay. So what we're going to do now is we're going to gather this idea and use it to construct something called a unit circle. I'm not going to do the derivation of how we kind of build the unit circle, because it's a bit beyond the scope of this class, but the idea is that I have a circle with radius 1, and that's centered at the origin. So if the radius is 1, I can right away label some points on this unit circle. For example, this point here is the point 1, 0. This point up here is 0, 1, negative 1, 0, 0, negative 1. How did I label those all so quickly? Well, if the radius is 1, I know this length is 1, right? So we've gone 1 unit horizontally in the positive direction. So the x-coordinate is 1. And we've gone 0 units up or down, so the y-coordinate is 0. Similarly for the other 3 directions. Is everybody okay with that idea? And what you should have talked about, or I think what the last test was, is that the points on this unit circle, the x's and y's, the x is cosine of this angle theta, and the y is sine of that angle theta. So any point on that unit circle, the x-coordinate, is going to correspond to the cosine of that angle, and the y-coordinate is going to correspond to sine of that angle. So, for example, if I wanted to do, say, sine of, like 55 degrees, notice that this is not something that I can do using my special right triangles, correct? Everybody can observe that, I hope. So how could I do something like this? Well, I'm going to go back to this picture up here. I'm going to start by estimating. Well, maybe I should start a new one. That's a little busy going on up there. Let me draw another one. I apologize for my poor circles. They're a little lumpy. So I'm going to start by estimating where 55 is on this circle. So this is halfway between 0 and 90, right? So that's 45. So 55 might be, say, like right here. Everybody's okay with that as an estimate? Yes? So how can I find, say, sine of 55? Well, I know this is cosine of 55, comma, sine of 55. So I can just kind of track this over and read it off here. So maybe this is about 0.85 or something. So if I had a super accurate or well-labeled XY axis and a good labeled circle, I could use that to estimate values of sine, cosine, and tangent just by reading off a graph of the unit circle. We'll pick up some more with this idea tomorrow. I don't have any assignment for you guys to do tonight. What I would ask, though, is if you still have worksheets to do to turn in, is you try to get those into me for tomorrow. Otherwise, that seems like enough for today. Have a good evening.